Hello and welcome back to the part 3 of the ongoing series on Pascal triangle, pyramid, PMR and NMR spectra, etc. And this part 3 is really going to be a very small video, very interesting, and we suppose that we are going to present something very new. Okay. So before we understand what that something new is, let us quickly have a review of what we have done in the first and second part of the course. In the first part, we have shown that the Pascal triangle is a representation of binomial expansion coefficient. That's why it is also called binomial triangle. But at the same time, this Pascal triangle represents the intensity ratio of proton magnetic resonance spectrum, because this is triangle, Pascal triangle, and this is the same binomial expansion triangle, or this is the intensity ratio triangle for PMR spin equal to half. But then in part 2, we have shown that Pascal pyramid, it is again a beautiful representation of trinomial expansion coefficient, that is A plus B plus C whole to the power n. But this pyramid does not represent the NMR spectra, NMR in the sense that spin I equal to 1, not half like proton. So this inequality or non-correspondence between Pascal pyramid and NMR spectra was explained in the part 2, and we have shown that this is the typical and really the true intensity ratio pattern for spin 1 nuclei, and which is not represented by Pascal pyramid. Say for example 1 2 1 2 1 2, but here it is 1 2 3 2 1. So we also explained that why this is a failure, and this is because of multiplication versus addition. In case of binomial or trinomial expansion, we multiply the terms a, b, or a square, b, etc. But in case of spectra, we do addition of the spin values, right? So that is the reason, and from understanding of basic physics and basic mathematics, we have explained in details why and how we should get this true intensity ratio. But the question is that, well, the Pascal pyramid, it does not represent the NMR for spin equal to 1. But can we get the spin I equal to 1 intensity ratios from Pascal pyramid itself by some little bit of extension, if not as such from the pyramid? Of course, without any detailed spin computation like the matrices, etc. we have discussed in part 2. So the answer actually is given by Mr. Orgho Bakchi, one of the YouTube channel subscriber and my friend. He wrote a comment after observing the part 2 that pause at 24.18 of the second part, and are the ratios really not there in the Pascal pyramid? If I reduce dimension of each triangle to a line, just think of animated shift of distant numbers gradually on the nearest baseline of the pyramid peak. What do I get by addition? And interestingly, then he went for addition in a definite pattern that I will show in a while, and he got exactly the true intensity ratio from the pyramid itself. So let us elaborate. Yeah, this is the true intensity ratio for n equal to I equal to 1. Now let us start with the pyramid. The first one, the second layer, 1 1 1. It's a triangle. Now as per Orgho's proposition, it is reduced to a line. So how? 1 and 1 comes as such, and then 1. So it gives a line, 1 1 1. The triangle gives a line, and that corresponds to the true intensity ratio, second row, 1. So that's good. But what about the next layer? So the next layer of pyramid is 1, 2, 1, 2, 1, 2. And then according to the proposition, the pattern goes like, well, 1 and 1 comes directly as such, and then this 2, 2 and 2, so they are also coming as such, because nothing else is there to be added. But here 1, 2, so they are added to give you 3. So 1 plus 2 is 3. So that is his observation, that is the pattern. And interestingly, that of course does match with the third row of the true intensity ratio, 1, 2, 3, 2, 1, 1, 2, 3, 1. Well, it may be a coincidence, but let us clarify it more from the next layer. Okay. Of course, I mentioned that the sum of the terms should be 3 to the power 1, or here it should be 3 to the power 2, that is 9. So you can check it. Now let us go to the next layer. Here again, this is the true intensity ratio triangle, and this is the fourth layer of the Pascal pyramid. So again, let us go along the same line. 1 and 1 comes directly, okay, and then 3 and this 3 left and right. Nothing else is there to be added. So 3 and 3 come as such. But next you see 3 and 3 vertically, 3 and 3, and here 3 and 3. So they are to be added to give you actually 6 and 6. Now you can guess what will be the last term, 1 plus 6. So that is 7. And interestingly, this is exactly what the true intensity ratio is from the fourth row, 1, 3, 6, 7, 6, 3, 1. Okay. So it's a beautiful correspondence. Okay, let us get one more layer. Here again, the sum of the coefficient of terms should be 3 to the power 3, that is 27, and it is exactly 2. So one more layer, let us check the fifth layer. So according to the proposition, we expect that the 1 and 1 will come as such, and then the 4 and 4 will come as such, right? And then you can guess 4 plus 6, 4 plus 6 here. So it should give you 10, and now 4 plus 12 and 4 plus 12, so it should give you 16. But the last one is 1 plus 12 plus 6. So it is 90. So that is exactly the ratio here, true intensity ratio. So really we are getting the intensity ratio from the Pascal pyramid itself. The nth layer gives you the nth line just by following the pattern provided by Mr. Orgo Bakchi. And one more. So here you can easily check it on your own that what you are going to get this time, the line, final line. And similarly, one more you can go even, and again you can check on your own what is going to be the line, right, for true intensity ratio for the seventh layer. So it produces all the layers through 1 to 7. So I think it's good enough, and we are ready to accept this pattern. And we can now claim, which is probably a very new one, that yes, Pascal pyramid can produce the true intensity ratio in NMR with spin I equal to 1. So next video, if you want, we can come back with spin I equal to 3 by 2. But till then, thanks for watching this part 3 small video. Thank you very much. I'll be very happy if you please come back with some comments whether the proposition as we demand it's new or not. Thank you very much once again.